Hi everybody, this is Mr. Yeoman, and today what we're working on is your airbag challenge. To summarize, your objective is to design an airbag that fills up using a chemical reaction in a similar way that actual airbags do. So you're going to be provided with a couple of pieces of equipment. First is a Ziploc bag, or in this case, it's actually a hefty bag. It's 1 quart. However, you might want to be a little bit more precise than that. So you'll have some opportunities on Monday to actually go through that and maybe take a look at some of these bags. The other piece that you're going to be having is a piece of tubing like this. We need this in order to measure the pressure inside the bag. You've been required what type of pressure has to be inside of the bag, so we need to make sure that you're actually addressing that. So within your design of your prototype airbag, you're going to have to figure out how to get this tubing inside of the bag and still have it be airtight. Because if it's not airtight, then you're not going to get the pressure that you want. Okay, so that's part of your challenge is to try to make that airtight. So you'll have some options this week in order to try to figure that out. But tomorrow, Monday, while I am gone, that would be a great time to kind of go through and think about some of these items and see if you can get some of these pieces to actually fit together and what you can come up with. All right. So that aside, the other item that you are going to have to figure out is how much reactant are you going to have to put into this bag. Now, these reactants have to stay separate initially, so that needs to be part of your prototype design. But not only do we need to keep them separate, because that's part of your design, you need to know how much you're going to have to put in there. So last week, we worked on a project where you were going through and calculating different amounts of items. So we've done each of these types of steps separately. So we've done them as single steps. And so we have a number of sample calculations. But at the end, what we're going to end up doing is putting all of these pieces together. So we're trying to figure out what do we know. So there's going to be a lot of pieces that we're putting together today to try to figure out what you need to do. Okay, so there's really two things that we want to figure out. Okay, so the first thing that we're going to try to figure out is how many grams of sodium bicarbonate are you going to need to use? Okay, that's our first question. So the way that we figure out, or the way that we use chemicals, is we have to weigh them out, so we end up determining their mass. We can't just look at it and say it's this many moles or there's this much of a substance here. So we're going to have to convert that. But we have another question as well. So we need to know how many milliliters or what volume of an acetic acid solution you will need to measure out in order to be part of your reaction. Okay, so that is those are really the two questions that we're trying to figure out. So how many grams of baking soda, how many milliliters of acetic acid are we going to end up using in order to make this reaction work? So there's a number of things that we need to know in order to figure that out. So one of the things that we need to do is figure out how many moles of product we're going to have. So last week we figured out the equation for baking soda and acetic acid, which we had determined was sodium bicarbonate, that's baking soda, plus acetic acid. And again, you can write this different ways. I'm writing this in one of the organic ways. Since this is an acid, then I have the acetate ion here, and I have a hydrogen that is going to be easily removed. Acids are hydrogen donators. Sometimes it's written with a hydrogen up here. It really just depends on your preference, but at the end of the day, they're all the same thing. You may be writing it as C2H4O2. That's also equally as valid. So it really doesn't matter how you write it. I just want you to recognize that this is the formula that I'm using right now for acetic acid, and this is the formula that I'm using for baking soda, sodium bicarbonate. Okay, so in our activities, we figured out that the products that were being made were carbon dioxide, water, and then we had some ions, so we had sodium ions and we had acetate ions. Now, we don't really care about those. Those are going to dissolve into the water, and that doesn't make our reaction. So the thing that we really care about is our carbon dioxide. That's the one that matters because that's the gas that is being produced. So we need to know how many of moles of carbon dioxide are we going to need in order to fill up our bag. Okay, so looking back at some of our previous reactions that we were working on, we derived the ideal gas law. Okay, so I'm going to come down here a little ways. And we knew that there was a relationship between pressure and volume. We knew that there was a relationship between pressure and temperature. Okay, and then we were also able to see that there was a relationship between pressure and moles. Okay, and so we put all of these together, and what we found was that we could make this into a single reaction called the ideal gas law. I'm sorry, a single equation, not a reaction. A single equation called the ideal gas law, which was PV equals nRT. Okay, now, when we have PV equals nRT, just like any mathematical equation, as long as we have 4 of our 5 variables, we can solve for that final one. And so that's what we're going to try to determine. Okay, so the pressure that we want to find, well, according to the rules from your activity here, then you need to have your airbag fill up to 5 kilopascals above atmospheric pressure, so above room temperature, or room pressure. So we're going to have to find out what the room pressure is, or atmospheric pressure. It's probably a better, more appropriate term. What is the atmospheric pressure? Plus 5 kilopascals. Okay, so that's what we need to figure out on that. The volume of the bag, well, we don't know that yet, and it kind of depends on what bag you choose to use. If you choose to use the bag that I'm providing to you, then you should be able to figure that out. Now, it does say that it's a quart bag. It's a quart size, but if we want to be a little bit more precise than that and saying a quart, first of all, a quart is not a valid measurement that we could be using. We're trying to measure this in liters. So we'd have to convert quarts to liters anyway. But in addition to that, what we could do is say, you know what, just because it says it's a quart doesn't mean it's exactly a quart. It's, when we talk about significant figures, how significant is that? And so you could try to determine how much gas is actually going to fill up in there. And so there are different ways to do that. And we looked at that last week a little bit. It said if I had a bottle, so an irregularly shaped bottle, if I had a very neat coffee mug that was a perfect cylinder, then mathematically we could use its dimensions to figure out approximately how much volume that cup will hold. But if I have an irregularly shaped container, so for example something like this, it's not the same size all the way down. It narrows. It does some other things. In addition to that, when you look at some containers, they can have very irregular shapes. So a better way to determine the amount of volume in that might be to actually put a liquid into it and measure the volume from that. So we're going to have to figure that out, and experimenting with it a little bit might be the best option. Trying to determine, all right, if I put a certain amount of volume of water into my bag and then pour that into a graduated cylinder, I can measure how much volume is in this bag. Okay, so that is an experimental value. Okay, the number of moles, well, that's what we're trying to find. Okay, that's our unknown. So we want to find that. R is a constant, and T would be the temperature of the room. But we need to make sure that we are measuring this in Kelvin. Okay, so we don't want to put that into our equation as Celsius or Fahrenheit because that's going to totally throw off your numbers and you're not going to have the right number of moles. This constant, there are a couple different constants that I'll come back to here in just a minute. And then we have our experimental variable, our volume. So you have to figure that one out just by measuring it and trying to see what volume does this bag hold. And then the last one is trying to determine the room pressure, the atmospheric pressure, and then increasing that by 5 kilopascals. Okay, so we can determine that using some of the equipment here in the room. We can determine that room temperature, and that should be fairly easy to do. Okay, the one that may be a little bit more difficult is trying to determine the constant, because there are a couple different constants, but this pretty much gives it to you because we're working with kilopascals. And so this is one of the constants. I've taught you both constants. One is measured in kilopascals and the other one is measured in atmospheres. And really, if we wanted to, we could go into other numbers like torr, or millimeters of mercury or inches of mercury. There's a number of different variables that you could put into this, but since we're working with kilopascals, and we're going to be using this 8.314. And then our label for that will be liters, liters, kilopascals over mole times Kelvin. Okay, so there's our number that's going to go there. So our N, that's going to be moles. This one has to be liters because that's going to match up with our constant. And then up here we have kilopascals. Okay, so we have all of our labels that need to go in there, and so you're going to have to figure those out. But once we know that, then we're going to be able to figure out some of these other items. So coming back up to the top here, if I know how many moles, using our ideal gas law, we can determine the number of moles that we're going to produce from this equation. And so once we know that, then I can set that equal to both of these questions, both of these things that we're trying to find out. So I don't know what that is right now, so I am just going to put y for my variable, moles of CO2, because that's what I figured out. That's what, when I set this equation up, and in order to do that, all I have to do is, just like any other math problem, I divide out the things that I don't want, and so I would end up with N equals PV over RT, okay, because that, I just divided out my RT. What I do to one side, I do to the other, so I end up with PV divided by RT. That RT cancels out, so I have N on one side, PV over RT on the other. I plug that in. Once I know this value, I'm going to plug this right in. Actually, I'm going to change this right at the top here. I'm going to change that to N, because that's really what our variable is down here. So I'm just going to keep the same variable. Sorry if that was confusing for you. I apologize. Okay, so I have my number of moles of CO2. And once I have that, we can use all of the knowledge that we have gained over the last couple weeks in order to convert this. Because looking at your booklet that I gave you, one of the pages that I have is that conversion chart. Sorry, is that conversion chart. And so if I know that I have a number of moles of one thing, so that would be a number of moles of CO2, and I need to get into grams of something else, then I can go from moles of CO2 to moles of sodium bicarbonate up to grams of sodium bicarbonate. Okay, we have the skills to do that. We've done each one of these steps individually. Now we're just putting them together. Okay, we can do the same thing down here because, again, we're looking for the same item, the number of moles of CO2. This one will be a little bit different because we're not looking for grams. Okay, we are looking for a volume of a substance. And I'll lead you through that one again. So doing the same thing, we have moles of CO2 into moles of acetic acid. And then from moles of acetic acid, we can turn that into something else using the molarity of our solution. We did something like this on Friday. So setting that one up, I know that I can go from moles of CO2 into moles of acetic acid by using the mole ratio. Okay, and in my equation, my mole ratio is very, very easy because it's 1 to 1 to 1 to 1 to 1 to 1. Okay, everything is already balanced. So there's not a whole lot of work to do on this one. Okay, so this is just going to be a 1-to-1 ratio. I know that moles of CO2 are going to be on bottom because I want to cancel that out. And I know that moles of CH3 COOH is going to be on top. Okay, so that's going to be my acetic acid. Okay, but I don't want it to be in moles. I want it to be in milliliters. Okay, last time we were converting to grams. Now we want to convert into milliliters, and that becomes a little bit more of an issue. And so, just as a repeat from last week, one of the things that we were looking at is that molarity is a measurement of concentration. And so molarity is moles divided by liters. Okay, so if I have a concentration of a 3.0 molar solution of acetic acid, then what that would mean is that I would have 3 moles of acetic acid for every 1 liter of solution. Okay, so the reason I chose 3 milliliters is, or I'm sorry, 3 molar solution is because that is what is in your equation here, or in your challenge here, is that you can use a maximum of 100 milliliters of 3 molar acetic acid and 2 grams of sodium bicarbonate. So that's why I chose that. So now I could just plug this in right up here. Okay, and then I could put 1 liter on the bottom, except I got a little bit ahead of myself here because what I put is moles on top, and what I really wanted was for moles to be on bottom. So I make mistakes too. So I want my 3 moles of CH3 COOH on bottom here, but I was going to put liters on top. Now that would be fine, except I wanted my answer to be in milliliters. Now, you could still write it in liters, then just convert later. It really doesn't matter. The other thing that you could do is, instead of putting 1 liter here, I could put 1,000 milliliters, since those are the same units, and then I just solve, and I've determined what I want. Okay, so that's just kind of a quick run through on that, but what I'd like you to do today is work with your groups and try to determine some of the things that you're going to want in your reaction, in your equation. Determine how much of the sodium bicarbonate and acetic acid you're going to want. But keep a couple things in mind. As you're doing this project, how can you determine how many moles of carbon dioxide you will need to fill your airbag to 5 kilopascals above atmospheric pressure? Okay, so we've kind of gone through that. But just think about what types of equipment would you need, what types of information will you need, because I haven't given you everything that you want to be using. The design requirements and constraints of your project limit you to using 10 grams of sodium bicarbonate. Um, but does that mean that you have to use the sodium bicarbonate in a solid form? Okay, are there other options? So what might those alternatives be? I'm not saying that you have to do it that way, but it might solve some problems for you that you may have picked up during our last activity. Okay, the design requirements and constraints limit you to using 100 milliliters of 3 molar acetic acid. That's the maximum that you can use. But do you have to use that concentration? Okay, what else could you do? What are some alternatives? Do you have to use all of that solution? It really just depends on what you want to do, and you can kind of change the way that that works. And then what other design requirements and constraints are important when deciding how to design your airbag? Okay, so I kind of wanted today, Monday, to be an opportunity for you to work through and try to revise the airbag design that you had previously, and then maybe getting some numbers that you can start figuring that out, and then later on this week, we'll be able to actually start building that airbag. Okay, so if you have questions, please let me know. Otherwise, I want you to try to figure out some of those numbers using that stoichiometry and determine how to make your airbag work as best as possible. Thank you.